In this video, we will explore the world of data through the eyes of science. Data science is much more than just coding and building models. It is an art of finding meaning in oceans of data and predicting outcomes. This video will cover the following topics. Data science in today's world, why we need data science and what are the business, market, and job opportunities of data science. We will then discover the 4 pillars of data science. We will discuss the basics of what is probability and statistics. We will then learn about linear algebra and one practical usage of linear algebra with an example. We will then dig our path into machine learning. We will learn what are the types of machine learning. We will understand what is supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning as part of machine learning. We will learn the 6 steps of data science lifecycle. Finally, we will build a Python code of a linear regression model. If you find this video useful, please like and share this video. Subscribe to my channel Software Flux to learn more about data science and other trending technologies. The field of data science has grown rapidly in recent years, and professionals who can analyze and interpret large volumes of data are in high demand. The job market for data scientists is very strong, and many industries are looking for people to help them make better decisions based on data. One reason the demand for data scientists is increasing is the increase in data produced by companies. With the rise of digital technology and the internet, businesses have access to more data than ever before. This information can be used to gain insight into customer behavior, market trends, and other important business influencing factors. But the volume of data can be overwhelming, and many companies lack the skills and tools to analyze it effectively. This is where data scientists come in. They have the knowledge to collect, analyze, and interpret to help businesses make informed decisions. Another reason for the strong job market for data scientists is the rapid development of machine learning and artificial intelligence technology. These technologies are becoming increasingly important in many industries and require skilled professionals who can develop and implement machine learning models. Data scientists with expertise in machine learning and artificial intelligence are in high demand because they can help companies harness the power of these technologies to gain insights and improve business operations. In terms of job opportunities, there are various roles in the field of data science. Some common roles include: data analysts collect and analyze data to identify patterns and insights. They often use tools like Excel, SQL, and Tableau to analyze data and create visualizations. Data scientists use advanced statistical and machine learning techniques to analyze and interpret data. They often have expertise in programming languages such as Python or R and can build machine learning models. Business analysts use data to help companies make informed decisions about strategy, operations, and other business areas. They often work closely with stakeholders to understand business goals and identify opportunities for improvement. Machine learning engineers create and deploy machine learning models in production environments. They often work with data scientists to turn machine learning models into scalable, production-ready systems. In addition to a strong job market, studying data science can offer many personal and professional benefits. Data science requires unique skills including critical thinking, problem solving, and analytical skills. Studying data science can help people develop these skills and become better problem solvers in a variety of contexts. In addition, data science can be applied to many industries and fields, meaning that people with data science skills can work in fields ranging from healthcare to finance and marketing. The 4 pillars of data science are: probability and statistics, linear algebra, machine learning, and computer science. Probability is a mathematical subject that can be used to determine or predict the probability of an event. The probability of the event is given a value of 0 to 1. If the given value is 1, it means that the event will happen with absolute certainty. On the other hand, if it is 0, it means that the event is unlikely to happen. Thus, the certainty of the occurrence of the event is high and its probability is higher. Statistics is another mathematical subject that mainly deals with data. It helps to conclude data because it has procedures for systematically collecting, classifying, and presenting data. Analyzing and interpreting detailed data helps to gain additional information. In the study and investigation of an event, the probability is used to measure the likelihood of an event occurring. On the other hand, statistics are used to look at patterns in data samples to conclude the population. Therefore, you should consider that statistics are not completely independent of probability, because statistical analysis involves probability distributions. Since both statistics and probability have their roots in mathematics, calculus is needed as a tool for quantitative analysis. The use of computers is also necessary to perform complex calculations during statistical data processing. Linear algebra is a mathematical subject that deals with the theory of systems of linear equations, matrices, vector spaces, and linear transformations. Linear algebra is used critically in almost all marginal areas of science. In practice, most problems are solved by linear models. Most of the more complex scientific problems are converted to vector and matrix problems and then solved using linear models. In the world of data, especially big data, linear algebra can be very convenient for processing huge data sets to perform many practical transformations, such as graphic transformations, phase transformations, object detection and tracking, audio and image compression and detection, blurring and signal to process. An appropriate statistical computing technique can be used to solve a certain business problem. These algorithms can use either iterative methods or linear algebra techniques for computation when working with data. Linear algebra serves as the computational engine for most data science problems because of its performance advantages over iterative methods. Let us illustrate linear algebra with an example. Three people denoted by P1, P2, P3 intend to buy some rolls, buns, cakes and bread. Each of them needs these commodities in differing amounts and can buy them in two shops S1, S2. The prices for rolls, buns, cakes and bread are different in different shops. Which shop is the best for every person P1, P2, P3 to pay as little as possible? Amount spent by the person P1 in the shop S1 is 6 multiplied by 1.50 plus 5 multiplied by 2 plus 3 multiplied by 5 and 1 multiplied by 16, which equals 50. Similarly for shop 2 it is 6 multiplied by 1 plus 5 multiplied by 2.50 plus 3 multiplied by 4.50 and 1 multiplied by 17, which equals 49. Calculation for all other people in shops, we get the following table. Hence, it is optimal for the person P1 to buy in the shop S2, for the person P2 in S1, and the person P3 will pay the same price in S1 as in S2. In 1959, Arthur Samuel defined machine learning as the field of study that enables computers to learn without being specifically programmed. Human analysis of certain data requires large expenses, time, and effort. The amount of data offered is huge and it is versatile and fast. Human intervention is not sustainable. Human knowledge is not always explainable, for example speech recognition, image processing. The solution must be adapted to the specific case, for example user biometrics. IBM created a chess program called Deep Blue. Chess grandmaster Garry Kasparov competed with Deep Blue in 2 chess matches in 1996 and 1997. In the first tournament in 1996, the old champion Garry Kasparov won. And in the second tournament played in 1997, Deep Blue won 3.5:2.5. Types of machine learning. Supervised learning is used in applications where labeled historical data predict likely future events. Unsupervised learning is used when historical data is unlabeled and is used to find unknown patterns in the data.
Semi-supervised learning is used in the same applications as supervised learning, where both labeled and unlabeled data are used for training. Reinforcement learning works by discovering which action yields maximum reward through trial and error. It is often used in robotics, gaming, and navigation. Supervised learning is one of the most important approaches in machine learning, a subfield of artificial intelligence. It involves training a machine learning model on a labeled dataset where each data point is associated with a specific label or outcome. The goal of supervised learning is to learn a mapping between input features, also called predictors, and output labels or classes so that the model can make accurate predictions for new, unseen data. In supervised learning, the input data is usually represented as a set of feature vectors or attributes that describe the features of the data points. For example, if we build a model to predict house prices based on various features such as location, size, number of rooms, etc., the input data would consist of a set of houses with the corresponding feature vectors, and the output markers would be the corresponding sales prices. The training process in supervised learning involves feeding the model labeled training data and adjusting its parameters to accurately predict the output marks for new unseen data. This is usually done by minimizing a cost or loss function that measures the difference between the model's predicted output and the true labels. Once the model is trained, it can be used to make predictions for new, unknown data by applying the learned mapping from the input features to the output labels. This process is called inference and involves applying the model to the new input data to obtain a predicted output label or class. Supervised learning is used in a variety of applications, including image classification, speech recognition, natural language processing, and recommender systems. It is a powerful and versatile technique that has enabled significant advances in many fields and continues to be an active area of research and development. Unsupervised learning is a type of machine learning in which an algorithm learns patterns and relationships in data without requiring labeled or pre-categorized data. Unlike supervised learning, in which the data is labeled with the expected outcome, unsupervised learning algorithms attempt to detect hidden patterns and relationships in the data without knowing the expected outcome in advance. In unsupervised learning, input data is typically fed into an algorithm, which then attempts to discover and learn patterns or relationships in the data. These patterns or relationships may be in the form of clusters, groups, or associations and provide insight into the underlying structure of the data. Clustering is a popular unsupervised learning technique in which the algorithm attempts to group similar data points into clusters. This can be useful for discovering relationships between data points and identifying patterns in large data sets. Another common technique in unsupervised learning is dimensionality reduction, which aims to simplify complex data by reducing the number of dimensions while preserving the important features of the data. This can be helpful in visualizing and analyzing large data sets and reduce the computational cost of subsequent analysis. One of the challenges in unsupervised learning is evaluating the effectiveness of the algorithm. Unlike supervised learning, there is no clear benchmark to evaluate the performance of the algorithm because there is no expected output to compare the results against. Instead, unsupervised learning algorithms are typically evaluated based on their ability to identify meaningful patterns and relationships in the data. Unsupervised learning has applications in many fields, including image and speech recognition, natural language processing, recommender systems, and anomaly detection. By detecting hidden patterns and relationships in large data sets, unsupervised learning can provide valuable insights and help automate decision-making processes. Semi-supervised learning is a type of machine learning that uses both labeled and unlabeled data to train models. It is an effective approach for scenarios where the cost of labeling data is high or where labeled data is scarce. It uses a small set of labeled data to guide the learning process, and then it learns from the larger set of unlabeled data to improve the accuracy of the model. Natural language processing, NLP. Semi-supervised learning can be used to improve the accuracy of language models by training them on a large amount of unlabeled text data. Computer vision. Semi-supervised learning can be used to improve object recognition by training models on large amounts of unlabeled images. Fraud detection. Semi-supervised learning can be used to detect fraud by training models on both labeled and unlabeled data, allowing them to detect unusual patterns and anomalies. Bioinformatics. Semi-supervised learning can be used in gene expression analysis, where the cost of labeling data is high, to identify the underlying patterns in the data. The reinforcement machine learning algorithm is a reward-based and immediate feedback technique. Here, the machine's goal is to maximize the numerical reward at every step. In the process of learning, the machine is not provided any supervision as opposed to the previous machine learning algorithms discussed so far. Instead, the machine is expected to figure out the optimum actions which will reap the maximum reward at each step, all on their own, without any interference. The actions that the machine takes at each step might not only affect the immediate reward but may also affect all the subsequent rewards. The ultimate aim is to reach the max possible reward in the least number of steps. Thus, trial and error search methodology and immediate feedback in the form of a numerical reward are the two main characteristics of reinforcement learning. An example of reinforcement learning would be when a machine learns to play chess, decides whether a move is right by planning the possible moves or anticipating the corresponding counter moves, and finally chooses one based on a reward-based appeal for a particular position or set of moves. Another such example is when a trash collecting bot's charge is about to reach critical levels and it needs to decide whether to clean one more room before reaching out for the charging station or to immediately rush to the nearest charging station. The decision taken by the bot depends on the ease with which it can reach the charging station, based on its prior knowledge. Following are some of the algorithms of machine learning. Six steps of the data science life cycle are: 1. Define the goal where you identify the problem to be solved. 2. Collect and manage data where you identify the information needed. 3. Build a model where you find patterns in the data that leads to the solution. 4. Evaluate the model, including validating whether the model solves the problem. 5. Present results and the document, including establishing how the problem can be solved. 6. Deploy model is where the model is deployed to solve the problem in the real world. Let us quickly create one model using Python. We start by importing the required libraries of NumPy and scikit-learn's Linear Regression module. We define our input features, x, as a 2D NumPy array with 3 rows and 2 columns, and the output variable, y, as a 1D NumPy array with 3 elements. We create an instance of the Linear Regression class and assign it to the variable model. We use the fit method of the model object to train the model on our input features and output variable. We define a new set of input features, x_test, and use the predict method of the model object to generate a prediction for each row in x_test. We print the predicted output values, y_pred, to the console. In this problem, the model was trained to learn the relationship between the input and output. The model learned that the output in every row was addition of inputs. 1 plus 2 gave 3. 3 plus 4 gave 7. 5 plus 6 gave 11. The model, when asked to predict the output for inputs of 7 and 8, the model gave the output 15. Similarly, when the model was asked to predict the output for inputs of 9 and 10, the model gave the output 19. To get to learn more about data science and other trending technologies in the computer industry, subscribe to my channel, Software Flux.